Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A level, Unit 4 Chemistry for October 2021. This is Section A. So Section A is basically 20 marks. I will go straight to the first question. Question 1 says, the decomposition of ammonia is catalyzed by tungsten metal. This is the equation for the reaction, as you can see, this one here. So they say this reaction has zero order kinetic. It's a zero order kinetic, so has zero order kinetics. It means total order is zero. When they say the reaction has zero order kinetic, it means the total order is equal to zero. So again, remember, how do you write the order with respect to a specific, basically the rate equation is usually written rate is equal to K in the concentration of reactants, power the order. So since here we have one reactant, it's going to be written like this one here. As you can see, rate is equal to the rate constant, concentration bracket, we put ammonia, power order 0. And since they say the total order is 0, it means the order with respect to ammonia is also going to be 0. Therefore, any number to power 0 is 1. Rate becomes equal to K. So here, when they ask what is the rate equation for this reaction, the rate equation should be rate is equal to K, since this is going to be order 0. Question B says, what are the units of the rate constant K for this zero order reaction? Again, let's see. Remember, rate is equal to concentration over time. And that is equal to mole per decimeter cubed divided by second. So it should be mole per decimeter cubed per second. And since here we see rate is equal to K, it means the unit for K should also be mole per decimeter cubed per second. So the answer here should be a C. Let us go to the next question. Part D says, which of these graphs represents a zero order reaction? One thing we need to know is first look at the axis. Here we have red, concentration. And we know for zero order equations or zero order reactions, the rate can either be, the graph can either be like this one here where we have rate over concentration is going to be a flat line, or concentration against time where we're going to have a horizontal slanting line like that. So this is zero order and that is for zero order. So we have to look through all the answers given A, B, C, and D and find out which one matches with the ones we have to remember. So it means based on the data we have, like this one here and this is the example, the correct answer should be A. And again, remember from your textbook, there is a graph drawn like this. You have that, you have that, you have that. This is the rate over concentration. When you talk about zero order, this is going to be first order, and this could be second order. There is also a concentration time graph. Let me draw it. If you have concentration here against time, and in that case, you have a line coming down like that, that is zero order, and first order and second order are going to be coming down like this, although first order is going to have constant half-life, which can be easily predicted. Now, how do we predict a second order from this reaction, from this graph here? You can plot again and plot rate against concentration squared. If it's a straight line passing through the origin, then that can tell you it's second order. So these things you have to memorize them from your theory. These graphs, this graph here, that graph there, and this graph here, you have to memorize them from your theory in order to be able to answer any question that comes on this topic in your exam. So I will continue to question 2. It says, what is the effect of increasing temperature on the average energy of the particles in a reaction and on the activation energy of the reaction? As you know, when you increase the temperature, there is more kinetic energy. It means the particles are going to be, the energy they possess is going to be increased. So the average of the average energy possessed by the particles is basically going to be increased. However, the activation energy is never affected by when you increase the temperature. So the answer should be D, because D gives us both the right things we're looking for. Energy possessed by the particle will increase. However, activation energy can never be affected by increasing temperature. So let's go to question 3. Question 3 says, ammonium nitrate is very soluble in water. So here they've given us ammonium nitrate, and this is the equation for its solubility. When you combine it with water or react it with water, we get the ammonium ions, as you can see here, and the nitrate anions. So they say, what is the best explanation for this? So since solubility in water will depend on how the ionic bond is going to be broken in this case, actually. So the energy required to break that ionic bond has to be provided. Also, solubility. For solubility to occur, the S total for that specific reaction should be, or for this solubility, should be positive. And since the S total is equal to the S system plus the S surrounding, versus the S surrounding is equal to this, so we can say the S total is the S system, as we can see here, minus delta H over T. Looking at this reaction, the forward reaction is positive, so it means the delta H is going to be positive 25.8, divided by the temperature. If the reason as to why this is going to be negative but a smaller negative, it is because the numerator is 25.8, which is actually small. So dividing a small number by a bigger number, or temperature is going to be, of course, 298 and above, by a bigger number, and this is a standard condition, so it should be 298, it creates an overall small negative number. And since we have a small negative number, yet when you look at this reaction, the S system is actually positive. It's going to be greater or positive because we see a solid dissolve to produce aqueous, so there is more disorder or there is increase in entropy. We know the S system is going to be positive, so this is positive, while that is a small negative. A positive minus a small negative will create a positive here, and therefore our answer should be D, which says the entropy change of the system is positive. That is the only reason as to why this should be able to dissolve, because that the S surrounding is negative. For this to be positive, this must be positive. That is what we're looking for. So the answer should be D. Let's go to question 4. Question 4 says, the decomposition of calcium carbonate is an important reaction in the manufacture of cement. What are the signs of the entropy change of the system, the S system, and the entropy change of the surrounding, the S surrounding? Again, we're going to look at this. So looking at this, we can see that a solid is converted into one solid and a gas. Since a solid produced a gas, we can confirm that the S system is going to be positive because there is increase in disorder. If a solid is converted to gas, the gaseous particles are more mobile, meaning there is going to be more disorder, so the entropy of the system increases. And again, to remind you, remember, entropy of a change in entropy of the system should be the entropy of the products minus the entropy of the reactants. Since products have greater entropy than the reactants, it means the S system is going to be positive, as you can see here. And since the S surrounding is negative the H over T, and this is an endothermic reaction, it means this value here is going to be negative. That is why we see here. So the S surrounding will be negative no matter what, because that delta H is positive. So the answer should be B, because it satisfies both answers. Let's go to question 5. They say the standard molar entropy, this is the standard molar entropy of a substance. So they want us to select which statement satisfies this. They say it's not affected by changes in state or changes in temperature. No, it will be affected. It's going to be affected by of course, the change in temperature as well as change in state. Here they say only changes when the temperature changes. No, when a state changes, maybe something changes from a solid to liquid, you're going to have a different molar entropy. So only changes when the substance changes state? No. Changes when temperature changes and when the substance changes state. That is correct. I will go on to question 6. Question 6. The water-gas reaction is used in the manufacture of hydrogen. So here we can see there is carbon, there is water, and then carbon monoxide produced as well as hydrogen. They ask, what is the equilibrium constant Kc for this reaction? Kc, I wrote the explanation down there, but let me just write it again here. So here we can say Kc is going to equal to the concentration of the products multiplied, and then here divide by the concentration of the reactants. Now, since we have a solid, we're going to ignore the solid. This is going to be ignored. However, water being a gas at the reactant side, it's not going to be ignored, so we have to put it in here. So the Kc value should be, as you can see here, it's going to be the concentration of carbon monoxide times the concentration of hydrogen divided by the concentration of water. When we are writing Kc, we ignore solids, but we cannot ignore water at the reactant side if it is in gaseous state. Part B says, what happens to the equilibrium constant of the forward and reverse reactions when the temperature is increased? Again, let me take you back above here. We can see, because this is what we have got, This is the equation for Kc we have seen. So Kc forward, Kc reverse. Kc forward is going to be like this. Let me write it here. Forward Kc is going to equal to the concentration of carbon monoxide, like we have got hydrogen, divided by the concentration of water. However, Kc backward, this is forward. Kc backward is going to be the concentration of water divided by the concentration of carbon monoxide, concentration of hydrogen. Because when you are going backward, of course, the reactant is going to be carbon monoxide as well as hydrogen. So in order to predict how the forward Kc and the backward Kc are going to be affected, so we're going to look at the reaction. Since we see it is going to be endothermic in the forward direction, increasing temperature will increase or will shift equilibrium to the side where they are, to the forward reaction, of course, to the endothermic side, meaning when the temperature is increased, more products are going to be produced, and therefore the Kc of the forward reaction is going to increase, as you can see here. Now let's look at the Kc backward. When we increase the temperature, the reactants are going to decrease, so there will be less water. And that means because the numerator here is going to be less divided by the denominator, which has increased, it means the Kc backward or the backward Kc or reverse Kc is going to be decreased. So here we can see B is going to be the answer for this. And again, you have to be able to know this reaction in order to be able to predict what is going to occur here. I'll go to question 7. Question 7 says the diagram shows a Born-Haber cycle for magnesium chloride. So as we can see here, okay, let's see. The first question says, which of these is the electron affinity of chlorine? If we are looking for electron affinity of chlorine, is when a chlorine gaseous chlorine atom gains an electron to become a gaseous ion. That is electron affinity. So when we look, here chlorine is still an atom. However, here it has become an ion. So since it's 2 moles of chlorine converted into 2 moles of chloride, the electron affinity here is going to be Y. However, this question is asking us for chlorine. Electron affinity is when 1 mole, in this case, it has to be Y over 2, and that is why B is the answer. The one required here is Y, but since it's for 2, to find the one for 1, you have to divide it by 2. So it should be Y over 2. B is the answer for that part. And then here they ask us which expression gives the lattice energy for magnesium chloride. I want to take you back a little bit here. Let me use a different pen. So if we are looking for lattice energy, which is this, to find lattice energy moving from here to here, we are going to go all the way backwards until this point here. So it's going to be lattice energy will equal, because you're reversing, this is going to be negative Y. And then going backward, it's going to be negative X, negative W, negative V, and then plus a U. So it means lattice energy is going to equal to U minus the sum of all the other things. So when we come down here, we can see that this is going to be what we're looking for. Therefore, the answer should be A. I hope you can understand that. I will move on to the next question. So this question says, which energy change in the cycle does X represent? Now, I want to take you back to the cycle so that we can see where X is positioned. Okay. X is positioned here. Again, let me use this. It's positioned here, you can see. Now, when you look this side, we have magnesium gas converted into magnesium 2+. It means this has been ionization of magnesium. However, this is 2 times. So it's twice the ionization energy of magnesium. And then when I go back to this question, the answer should be the sum of the first, let me use this, the sum of the first and second ionization energies of magnesium. And you can see the answer should be C. That is kind of easy. So next we see question 8. When ethanoic acid and chloroethanoic acid are mixed and equilibrium is set up, the Bronsted-Lowry acid in these equilibriums are, so remember an acid is going to be a proton donor and the base is something that accepts a proton. So when we look at this, this is ethanoic acid. However, it has become something else here because it has gained a proton. And because it gained a proton, you can see there are 2 hydrogens here. It means this is going to be a base. It was a base on this side and it became an acid this side because it gained a proton. In the reverse direction, it's going to be an acid. In the forward direction, it's going to be a base. Now, when you look at this, because it donates a proton to become that, in the forward direction, it's an acid. However, in the backward reaction, it will be a base. So the only combination of the bromine acid and acids in this equilibrium are, this is an acid. Let me use this. This one here is an acid, and that is an acid. So the answer here should be a C. The next question says, what is the pH of 0.01 mole per decimeter cubed aqueous sodium hydroxide? So here to do this, we have to know that calcium hydroxide, that in calcium hydroxide we have 1 mole of calcium, but we have 2 moles of OH minus. If we have the concentration of this to be 0.01 mole per decimeter cubed, and it is the same volume, it means we can use the number of moles. The number of moles here, number of moles of this one here are going to be 2 times the number of moles of calcium hydroxide. So it means it's going to be 2 times, since number of moles is concentration times volume, so we can say concentration times volume. And again, since the concentration is going to be, the concentration for this one, let me try to find the number of moles here, is concentration times volume. The concentration is going to be constant, which is 0.01. The volume we do not know, so we consider this number of moles as 0.01 V. However, when I bring it down here, remember this is number of moles, so let me erase this. So this will be 2 times, this is going to be number of moles 0.01 V, so it's going to be 0.02, of course the volume, and this is number of moles. So since I'm trying to find the concentration will be number of moles over volume, which is 0.02 V, but the volume is still the same. It means this cancels out, and it's going to be 0.02. So basically, they are the same concentration, but the concentration of the concentration of the previous one is just going to be multiplied by 2 to get the concentration of OH. That is why you see I got here. So since we have the OH ion concentration, we can use that to find POH. Remember, POH is negative log of OH minus, the concentration of OH minus, which is negative log of 0.02. And using your calculator, you'll be able to get this. Now again, remember there is another formula which says pH plus POH is equal to 14. We can use this with our POH we have calculated here to be able to find the pH. So pH will be 14 minus 1.6989, which gives us 12.3011. And when we look at the answers here, it's only this that is closest. So when you round off, it's going to be, of course, 12.3. Let's move on to question 10. Question 10. Citronellol is found in rose and geranium oils. So this is the structure they've given us, this one here. So they say the type of stereoisomerism shown by citronellol is, stereoisomerism involves optical isomers, and then we have, of course, the geometric isomers. In optical isomers, we have a chiral center. Let me show you here. And the geometric isomers, of course, we have a carbon-carbon double bond with superiority or higher priority groups, basically. There is around the carbon-carbon double bond, there should be higher priority groups. So they're asking us for the type of stereoisomerism exhibited by this structure. I'm going to begin by drawing the carbon atoms present in this structure. And remember, I'm going to look at the carbon-carbon double bond first. Now, when you look at this carbon-carbon double bond, you can see that this carbon here within the carbon-carbon double bond does not have higher priority groups because this is a methyl and that is a methyl. And because these groups are similar, that is not a geometric isomer. So we rule out geometric isomerism because we need to have superiority in priority. So then to go for the chiral center to show that there is an optical isomer, so we need to look at the carbons present. So when you look at this carbon here, it has 3 hydrogens, so it's not chiral. A chiral center should have 4 different groups attached to the carbon. This one is a double bond, not chiral. That is not chiral, and this is not chiral. When we look at this, it has 2 hydrogens, so not chiral. Here 2 hydrogens, not chiral. Here 3 hydrogens, not chiral. Here we have 2 hydrogens, not chiral. 2 hydrogens on this, not chiral. And of course, it leaves us with this part here. Now, if you look at my displayed molecule, you can see that this carbon is attached to a methyl this side, another group this side, another group this side, and a hydrogen here. So that center is chiral, and therefore this structure exhibits optical isomerism only. There is no geometric isomerism because over here there was no higher priority group, so this was not a geometric isomer. It was just an alkene, not a geometric isomer. But over here we had a chiral center, so it exhibits optical isomerism. I will go to question 11. Question 11 says ethanol and propane. Again, ethanol is an aldehyde. Let me write it here. And propane is an alkane. So they say ethanol and propane have the same molecular mass, but ethanol has a much higher boiling temperature. When they say that organic compounds have the same molecular mass, we expect that they have the same strength of London forces. That is very important. So if they have the same strength of London forces, but one has a higher boiling point than the other, it means there is another intermolecular force that is causing that other molecule to have a higher boiling point. And in this case, since ethanol has a higher boiling point than propane, yet they have the same strength of London forces, it means the aldehyde, which is ethanol, can form stronger intermolecular forces that lead to the formation of the ability of having a higher boiling temperature. So there is another property they tell us here. Ethanol is fully miscible in water, but propane is almost insoluble. Now again, to be soluble in water, we need intermolecular hydrogen bonds to be able to form intermolecular hydrogen bonds with water. And as you know, an intermolecular hydrogen bond is going to be between a dipole and the other side. There is a dipole here and a lone pair. So we need a lone pair, we need a dipole. Since for alkanes like propane, there is no dipole, it means there is no chance of it forming intermolecular hydrogen bonds. Also, we have the ethanol. Ethanol has a carbon-oxygen, the carbon-oxygen double bond, and there is a dipole, as we can see. There is also a lone pair, or two lone pairs actually, of oxygen present on the oxygen, two lone pairs present on the oxygen, and that can be a good quality to help in the formation of intermolecular hydrogen bonds. So the question is asking which intermolecular forces of ethanol are mainly responsible for the difference in these properties. The higher boiling point is, of course, because ethanol has that carbon-oxygen whereby we have a dipole, and again, this is between ethanol molecules. Ethanol molecules cannot form intermolecular hydrogen bonds within themselves. However, because they have permanent dipoles, they can form permanent dipole, and that is why we can see that leads to the higher boiling point due to the ability to form permanent dipoles. Now, the greater solubility, because solubility is about dissolving in water, should be only due to hydrogen bonds as they interact with water molecules. So if you want to read further, what I wrote down here, you can see the same explanation. I will go to question 12. Question 12 says, an unknown aldehyde may be identified by measuring the melting temperature of the purified precipitate formed in the reaction with, of course, this is easy, formed with 2,4-dinitrophenylhydrazine. If aldehydes are undistinguishable because they have the same boiling point, what they normally do is they will react them with a 2,4-DNPH, which is 2,4-dinitrophenylhydrazine, and then the precipitates will be collected that are going to result. Those precipitates will be purified, and then their melting point can be determined. They will determine that their melting points are going to be different, and they can refer to the data booklet in order to confirm which temperature matches with which known compound. So basically, they can be able to distinguish the two or more different aldehydes or even carbonyl compounds. Question 13 says, butanoic acid may be prepared by the acid hydrolysis of. Now, by acid hydrolysis to produce a carboxylic acid, we can do two ways. Acid hydrolysis can be from a nitrile, or it can be from an ester. However, here we can see when they say propanenitrile, if it's propanenitrile is going to have only 3 carbons, so you cannot hydrolyze it to form 4 carbons. No, this is not possible. So what we need to do is, it means it has to be an ester, and that ester should be a butanoate, because remember, you are producing butanoic acid, and the butanoic acid, it means this group should come from the carboxylic acid, or this group is the one that is going to produce a carboxylic acid if you carry out hydrolysis. Now, the key thing is, because they said acid hydrolysis, we should know it should be an ester, which is a butanoate. So the only butanoate which is an ester is C, which is ethyl butanoate, and that gives us the answer for question 13. So I will go to question 14. It says, pterylene is a polyester derived from ethane 1,2-diol and terephthalic acid. they've given us the structure of terephthalic acid, and then they ask what is the structure of the repeat unit of pterylene. So all we need to do is to try and draw what is ethane 1,2-dioic acid, ethane 1,2-diol and terephthalic acid, in order to determine what the polymer is going to look like, or what the repeat unit of the polymer is going to look like. So here I try to show you the groups. Because it's polymerization, I put the terephthalic acid in the middle here, and then this side I put the ethane 1,2-diol, and the other side the ethane 1,2-diol. But remember, if the repeat unit should come from one terephthalic acid and one ethane 1,2-diol, it means one of them should be cut out. So when I simplify, and again, as these two are joining, wherever they join from, a water molecule is going to be lost, and the atoms are going to be connected. So when we lose a water molecule and we connect, we can see the repeat unit that is going to be produced is going to be this. And looking at the structure, we can see that A is the only answer. You can see in A we have one group from the ethane 1,2-diol and one group from the terephthalic acid. If you look here, we can see there is two groups from ethane 1,2-diol, two groups from ethane 1,2-diol, which is wrong. And here the carbon oxygen bond is arranged in a weird way. The carbon atom with the carbon oxygen double bond should be closest. So it should be carbon oxygen should be closest to the ring. This is wrong, that is wrong, and that is wrong, because they have more than two groups, which is not right. So the answer here should just be an A. And lastly, question 15 says the formation of esters and the hydrolysis of esters are reactions that are slow under normal laboratory conditions. So they ask what speeds up these reactions. If we want to speed up these reactions, of course, we're going to do use a catalyst. Now, because they have said formation of esters, which is esterification, and hydrolysis of esters, well, when we form an ester, it's esterification, we use sulfuric acid as a catalyst. So esterification uses acid catalyst only. However, hydrolysis of an ester we can do two ways. We can do acid hydrolysis, whereby we form a carboxylic acid and an alcohol, or we could do alkaline hydrolysis with sodium hydroxide, where we can produce a carboxylic salt and an alcohol. So it means for hydrolysis we can do two ways, either acid hydrolysis or alkaline hydrolysis. That is why the answer here should be B. This brings us to the end of section A. I hope to see you in the next video when we talk about section B as well as C. So thank you for being with us. Please remember to subscribe. See you in our next video.